Yes, so I'm going to talk about non-monotonic reasoning in natural language. And I'm going to start with a little bit of overview of the state of NLP in 2021. So over the last few years, deep learning led to breakthroughs in NLP. And if you get your updates from popular media, then you hear a lot about human level performance, or even tasks where we can already get better than human performance on various different complex language understanding tasks. And then for those of us working in this field, we often track progress by looking at leaderboards such as Superglue that involve a range of complex language understanding tasks. And as you can see here, since Superglue was launched 2 years ago, it's already been, the human performance has already been surpassed. But in practice, does it mean that NLP is solved? Well, not really. So one of the problems is that we seem to be measuring progress where progress is easy to measure. So we reduce complex language understanding tasks to simplified multiple choice or classification tasks. Here's one example: recognizing textual entailment, RTE, or in its newer name, natural language inference, NLI, is an entailment task, which is considered to be one of the most important NLP tasks. It is considered, if the model gets a good performance on this task, it is considered that it understands language. So here's an example, given the premise that 2 dogs are running on grass and the hypothesis that 2 animals run outside. The goal is for the model to determine whether the premise entails the hypothesis, contradicts the hypothesis, or is neutral. You cannot tell if the hypothesis is true or not. This is not as strict a definition as for entailment in logic or in linguistics. There's a little bit of hedging in the definition. It's whether a person reading the premise can likely infer that the hypothesis is true, or something like. There's some double hedging there. But that's the task definition. And neural models already get really good performance on this task. More recently, in the last 3 years, the dominating paradigm is to use pre-trained language models. So such language models include, for example, Google's BERT or OpenAI's GPT. And they have slightly different objectives, but in general, they are pre-trained to read a large text corpus, such as Wikipedia or the entire web. And then as a result, they learn about syntax, they learn about word meanings, some factual knowledge about the world, some common sense knowledge. And then this is used as the base or the representation for many different models for different tasks. And typically, they're also then fine-tuned or trained on specific data set to perform very specific narrow tasks, such as NLI. And the most standard thing to do that is by simply representing the input for NLI as some string with this. There's a premise and some separator token, and then the hypothesis, encoding it with the language model, such as BERT, and feeding it into a classifier, or MLP, to predict the class probabilities. And this is the very standard way. This is the way that most of the classification or multiple choice tasks work in NLP, and that gets you state-of-the-art performance. And then this step of fine-tuning is important, even though the representations already capture a lot of knowledge about language and the world from their pre-training. This fine-tuning step is responsible for the model to understand and learn to solve the task, or to basically learn a mapping from the input to the output. There are many problems with these settings. I usually continue this slide by introducing the fact that this doesn't actually mean that the model learns to solve the task, but that it learns some patterns in the data. But that's not actually the the focus of this talk. What I want to talk about is that these simplified tasks, they don't actually measure models on a lot of different reasoning abilities. And for instance, their ability to read between the lines or make tentative conclusions based on incomplete information, which are prevalent in natural language. And in particular, one aspect of reasoning that was mainly overlooked in modern NLP is non-monotonic reasoning. And I obviously don't need to introduce that here in this workshop, but I'm just going to mention the types of reasoning that we worked on. So we worked on defeasible reasoning, in which additional knowledge can invalidate prior conclusion. Abductive reasoning, which is reasoning about the most plausible explanation of given observations, and counterfactual reasoning, which is reasoning about changing outcomes given a change in condition or answering what-if questions. All of these tasks have been studied in classical AI or in many other fields, but often the symbolic methods that were used to address them were too rigid for the messiness of natural language, because natural language is often underspecified and ambiguous, and we have a lot of speakers have different interpretation. It's not very clear cut. So in this talk, I will discuss several recent papers in which my colleagues and I addressed non-monotonic reasoning with in natural language with modern NLP tools. So let's start with defeasible reasoning. So in defeasible reasoning, using the famous example, the premise that Tweety is a bird likely entails that the hypothesis that Tweety flies, unless we get additional information, such as, for example, that Tweety is a penguin. And like other modes of non-monotonic reasoning, it has been studied a lot in classical AI. But despite the focus of the NLP community on natural language inference, there was no work on defeasible natural language inference. And it is a very important ability. So I want to demonstrate just one example of an NLP task that could benefit from defeasible inference. So let's say you're building a model to summarize news events or some kind of an unfolding event. So the model might get new information that changes the prior conclusions or the previous parts of the summary. For example, and I hope this example is not triggering to anyone, summarizing what is known about COVID in the beginning of the pandemic. So in the beginning, it was reported that the virus could only be transmitted from animals, but then later on, it was confirmed that people can also pass it to each other. And over as the time passed by, more and more information was available, and some of the previous conclusions, if the model was building some summary, were already incorrect or inaccurate, and they needed to be updated. So this is one application of defeasible inference in natural language. I don't know of any models that actually does that for now. So in a recent paper, we targeted the task of defeasible inference in natural language. And this paper was led by Rachel Rudinger, who is now an assistant professor at UMD. So first of all, we extended the task so that we could have an update sentence that could either weaken or strengthen the hypothesis. So in this Tweety flies example, the weakener could be something like Tweety is a penguin, but then we could also strengthen the inference that Tweety flies if we get an update sentence that says that Tweety is on a tree. And so we collected data sets for this task. We augmented existing NLI data sets with these update sentences that we collected from people. And we had 3 different types of data sets. So one of them was a standard NLI data set, natural language inference data set. It was based on the SNLI data set, which is Stanford NLI data set. So for example, for the premise, a group of people sitting around a table with laptops, it might entail that they have a work meeting, and then we collected a strengthener saying that they're in a conference room and a weakener saying that they're in a library. Because if you're in a library, you're less likely to talk, and in a meeting, you need to talk. That was the first one. The second type of data set that we used was common sense inferences, specifically mostly about social common sense. So this is based on the atomic knowledge base. So you have an event with this placeholder for the subject. They have person X and person Y. Person X is the person performing the action, and person Y is an affected person. There's no person Y here, actually. So person X has a pool party, might entail that it's because person X wanted to hang out with friends. And then a strengthener would be something like it was person X's birthday, but a weakener could be something like person X was having a family reunion. So they're not meeting with friends, they're meeting with family. And the last type of data that we used was from another paper about social norms. And here there's no premise. The premise is just there's some general situation, and then the hypothesis is some social norm that needs to hold in this general situation. So for example, it is rude to comment on someone's weight. But then, and then that's especially true if this person is sensitive to their weight, but it is less true if you are their nutritionist. So after we collected the data, we defined 2 tasks, and then we trained a bunch of language model-based baselines. So the first task is the discriminative task. So here the model gets the premise and the hypothesis and the update sentence, and needs to determine whether the update weakens or strengthens the hypothesis. And actually, we got pretty good performance here, but it's not necessarily because it's easy. It's mostly because when you collect sentences from people, from crowdsourcing workers, or from people in general, there might be some biases in the way that they describe the strengtheners and the weakeners, and it's something that for models is very easy to pick up on. Even so, we also had a baseline in which we only provided the model with the update sentence, and it's still, or just I think just the hypothesis in the update sentence without the premise, and it still managed to get a good performance, which means that it's not actually solving the task in the way that humans do, because we need all the inputs, but rather it's just relying on some words that might be more typical for strengtheners versus weakeners. And that's a problem that is known in many NLP tasks, specifically in discriminative tasks in which one of the inputs was collected from people. So that's the less interesting task that we worked on. The more challenging one was the generative task. So here the model was given the premise and the hypothesis, and was required to generate either a weakening sentence or a strengthening sentence. And here the model, this was much more challenging, and the best model achieved about 60% accuracy, as opposed to more than 80% accuracy that humans got on this task. So there's plenty of room for improvement on this task. Let's look at some of, we analyzed the generated updates, and so let's look at some of the types of updates that were generated. So first of all, a large portion of them were correct. Here's an example for the premise: a man just roaming on the streets during night. And the hypothesis: a man is roaming the streets at night, drunk. So the strengthener that was generated is that the man has a beer in his hand. So that strengthens the fact that he's drunk. We had a lot of examples that were update sentences that were neutral. They needed to either strengthen or weaken the hypothesis, but in practice they did neither. So here's an example: person X pays person X or their own debt because person X wanted to be debt-free. And then the update sentence that was generated is that person X is in debt to the IRS. Now, to me, it looks neutral. Like it doesn't make person X want to be less debt-free or more debt-free. Some people may interpret that differently. Maybe it's even a strengthener. Maybe if you have a debt to the IRS, you even more want to be debt-free, or maybe less. I don't know, but it doesn't seem like a weakener. We had a lot of cases, or some cases in which the model was required to generate a weakener, but it generated a strengthener, or vice versa. We had some cases where the model just restated either the premise or the hypothesis. For weakeners, we had some cases in which the model generated a sentence that was contradicted the premise. So even when the model is required to weaken the hypothesis, the premise is still taken to be true, so it shouldn't contradict the premise. So for example, for the premise, person X picks person Y up at the airport, and the hypothesis before person X needed to get ready, the model generated person X is driving, generated the weakener, person X is driving person Y to the airport, which contradicts the fact that it was, that person X was driving to pick up person Y who's at the airport. In general, I think language models are not very good at, I don't know, like tracing the location of people, or these two sentences seem very similar. So it's likely that the language model just confused these two sentences. So moving on to the second part, which is about abductive reasoning. So in abductive reasoning, the goal is to come up with the most plausible explanation of what happened between incomplete observations. Here's an example from the ART dataset that we worked with. So for example, if we have if we know the past observation that Sarah wanted to make dinner for some guests, and the future observation that she had to order pizza for her friends instead, then we can hypothesize why that happened, and maybe come up with an explanation that she realized that she doesn't actually know how to cook. And abductive reasoning is also very useful for NLP. Again, this is an example application that is, I don't think is not commonly used in practice, at least. When we tell stories, we don't actually tell all the information. We just provide information that we consider complementary to the listener's knowledge, because we don't want to bore people or don't want to tell very long stories. And here's an example. This is from a news report from earlier this year. Tesla officially moved its headquarters from Palo Alto, California to Austin, Texas. CEO Elon Musk announced at the company's 2021 annual shareholder meeting. In April 2020, on a Tesla earnings call, Musk lashed out at California government officials, calling their temporary COVID-related health orders fascist and expletive-laced rant. In 2020, Musk personally relocated to the Austin area from Los Angeles, where he had lived for 2 decades. So in between these two bullets, the first two bullets, you might add the explanation that is that most people would infer that the health orders in California delayed Tesla's production and hurt the profits. So Musk decided to move the headquarters to a state with less restrictions. And you can go on with the explanation depending on how much you think the listener knows. Specifically, the task that we worked on is in a different domain. It's in a fiction domain. That's the example that I showed in the one of the previous slides from the ART dataset. So the goal is, the task is, the model is given the past and future context, and it needs to generate a hypothesis that is fluent with both of them, that could fit in between. And of course, you can just train a supervised model to generate the hypothesis given the past and future observations. The problem is that it's going to be domain specific. So if we train it on a data set of fiction, then we can't actually apply it later to news, for example. So our goal was to come up with a more generic model, and we developed an unsupervised model. So it was again based on language models. Specifically, in this case, we use standard language models as opposed to masked language models. Just to be on the same page, these models can be used for generating text. So for example, GPT, you can give it a prompt like Sarah wanted to make dinner for some guests. And then they encode this prompt and they output the distribution over the entire vocabulary for the next word. And then you can obtain that next word from the distribution by just sampling in various different ways. Let's say greedy sampling, just taking the word with the highest probability, and then feeding it back into the model as input to generate the next word, and so on, until you reach some number of tokens, like maximum number of tokens, or an end of sentence token. The challenge in developing a model for abductive reasoning that is based on language models is that language models are only conditioned on a past context. While in this task, we also needed to consider the future context. And indeed, if you let GPT-2 come up with the next sentence following the past observation, then it says that I'm going to grab some rice noodles, she says, which doesn't make sense with respect to the future observation that she ordered pizza. So our solution was to compute loss with respect to the future context, and then backpropagate the error to update the output. I know it's not very clear. I'm going to explain everything in the next slides. So this is a paper from last year, which was led by Karen, who's a PhD student at UW. So we developed DELOREAN, which stands for Decoding for Non-Monotonic Logical Reasoning. And it's based on off-the-shelf language models, and it is unsupervised. So for the abductive reasoning task, we define the inputs as X, which is the past context, like Sarah wanted to make dinner for some guests, and Z, the future context. She had to order pizza for her friends instead. And the model needs to generate a hypothesis Y, which is both a fluent continuation of X, but also satisfies the future context Z. The model consists of an initialization step, and then we iteratively move from backward to forward passes. In the initialization step, we input the past context into the language model. Sarah wanted to make dinner for some guests, and then we predict the next n token vectors. So we predefine an maximum length for the hypothesis. We don't actually sample the discrete words, so we don't have a sentence here. We just keep the soft representation of these vectors, which we call y tilde. So each vector in y tilde corresponds to the distribution over the vocabulary for a given token. The backward pass is responsible for instilling the task-specific future constraint Z into Y. So first, we continue inputting the future context Z into the language model. She had to order pizza for her friends instead. And then we compute loss with task-specific loss with respect to the current Y tilde and the future context Z. And we backpropagate the error to update Y tilde. We actually keep a second copy of Y tilde, which we call Y tilde backward. In the abductive reasoning task, the task-specific loss function tries to maximize the likelihood of the language model to generate the future observation Z following the past observation X and the generated hypothesis Y. And we get that by minimizing the cross-entropy loss. The forward pass is responsible for generating a continuation Y, which is fluent with the past context X. And it is almost identical to the initialization step because it starts with inputting the past context X and predicting tokens, except that now at every step, we mix Y tilde forward, that is the output of the language model, with Y tilde backward that was computed in the backward pass in a linear combination, and then we feed the mixed vector into the language model. So now we have both constraints, the past constraint and the future constraint, taken into account when the model is generating the next token. And the last step in each iteration is to generate a text. And so we do that by greedily decoding from each vector in Y tilde to obtain a word. So we can get something like, but she didn't know how to cook. So this process repeats for t iterations, and it takes some time to get good outputs, but we don't necessarily know which one of the t generated y's is the best one. So we also have a step where we select the best one, and what we want is y that is the most likely to follow the past observation x and to precede the future observation z. And we get that with the BERT model has an objective function of next sentence prediction, whether two sentences are adjacent. So we use that to rank the y's. In the paper, we also have automatic evaluation, but in general, in generative tasks, we don't actually have good automatic evaluation metrics. So the human evaluation is the more informative one. So I'm going to focus on that here. So we asked people to rate how coherent the generated hypothesis Y is with respect to the past context X and the future context Z, or each one of them separately and both of them together. And then what you see here is the average score across instances that we labeled and or evaluated, and across the different annotators. So 0 being the worst and 10 being the best. So this is the performance for, this is DELOREAN's performance. And we also compared it with other unsupervised models, and it outperformed them substantially. It was also competitive with supervised models, even though it's unsupervised. But all of this needs to be taken in perspective to the human performance. So you can see that there's still a large gap from human performance. So again, plenty of room for improvement on this task. Let's look at the example of 5 iterations of generations for this dinner example. So the first generation is she was thinking about the best way. That doesn't yet make sense. The second one is, however, her cooking skills were the only thing that could make it a success. Again, it's a little bit contradicting. It doesn't make sense. But something nice that happens from here onward is that because of the backward pass that instilled the future constraint, now every generation starts with a contrast word because there's some surprisal in the future context. But she couldn't because she was too busy with her work. That's already good. But she didn't have the money and she didn't have her own kitchen, but she didn't know how to cook. So all of the last 3 are pretty good, I think. Okay, moving on to the next part, which is about counterfactual reasoning, which we also addressed in DELOREAN. So in counterfactual reasoning, the goal is to reason about changes in outcomes given a change in conditions, or more simply, asking and answering what-if questions. Again, I want to motivate that with NLP applications that I don't think that in practice are actually doing any kind of counterfactual reasoning, but could benefit from that. So one of them is argument mining. If you have claim X that you want to make an argument against it, you can suggest that if X would have happened, that would result in some unwanted outcome Y. Here's an example. This is from a few years ago from a data set, an argument mining data set. It's a claim against China's one-child policy. And it says, if for any reason the single child is unable to care for their older adult relatives, the oldest generations will face a lack of resources and necessities. Very similarly, you could also use the same trick to detect misinformation or to refute it. So for example, so if you want to show that claim X is false, you can show that it entails claim Y, which is known to be false. So here's an example. I searched Twitter for face mask reduced oxygen, which was something that some people claimed in the beginning of the pandemic. And then I found this response from someone who said, if this was true, all the doctors and nurses doing 12-hour shifts for 6 days a week would be dropping like flies from wearing masks all day. Do some real research and stop spreading misinformation. So this is pretty cool. This is counterfactual reasoning in the wild. We targeted a data set called time travel, and it is similar to the abductive reasoning data set in terms of the domain. It's also using fiction. It's based on the same types of stories. Here, the data set contains a 5-sentence story. For example, Lisa was throwing a Halloween party. All her friends were dressing up. Lisa thought about being a wizard. Then she decided on a scarier costume. Lisa dressed up like a vampire. And then the second sentence is changed with a counterfactual condition. So now instead of all her friends were dressing up, we have it was a Game of Thrones themed party. And the goal is to generate an alternative new ending, which on the one hand adheres to the counterfactual beginning, to the revised two first sentences of the story, while on the other hand is very similar to the original story, only minimally edits it to be to adhere to the counterfactual beginning. So here's an example that was generated by DELOREAN. Lisa thought about how she would dress up as a Lannister, but she didn't want to look like a Lannister. She wanted to look like a Stark. Lisa dressed up like a Stark. So you can see here that some content is copied from the original ending, but some content is replaced with references to Game of Thrones. So the inputs for DELOREAN were, first of all, X, which is the counterfactual story beginning. So that's the new first two sentences of the story, and Z, which is the original ending, the 3-sentence ending. And the goal is to generate Y, the alternative ending. The future constraint here is that we want the representation of Z, the original ending, to be as similar as possible to that of Y, the alternative ending. That's a minimal edits requirement. So we do so by minimizing the KL divergence between the one hot representation of Z and the generated ending, the soft representation of Y tilde. The forward pass and the generation are the same as I showed for the abductive reasoning task. And then the ranking to select the best Y is also similar, except that now the Y that we generate consists of 3 sentences. So we also want to make sure that there's internal consistency between the sentences of Y. Among all the models that we tested, DELOREAN was the only model that achieved a good balance between adhering to the counterfactual condition, but only minimally editing the original ending. So what you see here is this area under the curve where we play with the parameter of how much we care about each one of the criteria. So we could care about only about coherence, or only about minimal edits, and everything in between is some mix of both of them. There's no single point here to compare, but it's more of a range. So looking at the pink model, Recon plus CF, that's from the original time travel paper. So this is a supervised model that gets access to the original ending as well as the beginning of the story. And then what it learned to do is it's very good at minimal edit, but it's not very good at coherence. And what it basically learned to do was to pretty much copy the original ending, which is not very smart, but it still gets a really good performance on minimal edits because it's minimizing the edits, but it's not a really good model. At the other end of the spectrum, if you look at the light blue model, this model is an unsupervised model that is based on language models, so it can only look at the past, the two first and the beginning of the story. And then because it's using language models, it's very coherent with the beginning of the story, but it doesn't take into account the ending of the original ending at all. So it's really bad at minimal edits. And then this purple line is DELOREAN, which is not the best at each one of these criteria, but it achieves a good balance between both of them. And this task also, the best model for this task also performs worse than humans. You can't see that in this graph, but it's in the paper. Okay, so I'd like to briefly discuss the challenges in the approaches that I presented today. Apart from the fact that I mentioned for each one of these tasks that we are nowhere near human performance. So first of all, we are using language models for everything now in NLP, and specifically in these models, we didn't use any external knowledge resource. So we're basically relying on language models as also the source of word knowledge. And while language models capture a lot of world knowledge, it's very inaccurate. It has very limited precision. For start, because they are trained in a distributional objective, language models are basically trained to predict a missing word in its context. So as a result, they tend to confuse semantically similar but mutually exclusive concepts. For example, if you let BERT continue, or if you query the substitutes for the mask and DirectX is developed by mask, then BERT basically knows that it should be a company name. It even knows what kind of company it should be. It's like a, I don't know, software company, but it predicts various different companies with similar scores, where the second one here, Microsoft, should be the correct answer. And that's just one example out of many. If you ask BERT about colors of things in the world, like, I don't know, what color is a dove, then it also predicts many different colors. It's very good at knowing the category of word that should be there, but it's not really good at being able to predict the exact correct answer. They're also not sensitive to negation, which is definitely a problem in reasoning tasks. The second problem is on the other side of the problem is so this was limited precision. The other side is limited coverage, and here there's a problem of reporting bias. So because these models learn from text, they're basically they assume that what is reported in text is what is true in the world. But it's not true, because people tend to speak more about the exceptional than they speak about the obvious. It's related to what I mentioned earlier, that we never actually provide all the information when we tell stories, because we assume there's some knowledge. So any kind of like common sense inference that is very trivial to everyone, it will not be discussed very often in text, as opposed to things that are exceptional. So this is one of my favorite examples. If you use BERT to try to estimate the probabilities or the frequencies of events and actions that people perform on a daily basis, it gives a very high probability of dying, even though it's something that only happens once in a lifetime. And that's probably because BERT was primarily trained on Wikipedia, and Wikipedia contains all these bios of people from history that are often already dead. And this is not just a problem with BERT. Also, if you use GPT or any of its variants to generate a story, it always somehow ends up with someone in the hospital or dying or something like that. And then in terms of the next steps, so first of all, we need to develop better models for this task that I presented today. And because as we saw, they're all still far from human performance. And these models didn't actually do any kind of reasoning explicitly, and few models in NLP do. So we might be able to do better if we incorporate a symbolic component. In general, the little work there is in NLP on neurosymbolic models mostly focuses on neural computation with some symbolic knowledge from knowledge graphs, which is great. But the alternative of also developing symbolic component computation and stitching together with some neural networks is also promising. Of course, it is hard because, as I mentioned earlier, language is very fuzzy and underspecified and ambiguous, so it's kind of hard to develop symbolic models for language. And the second thing we need to do is, once we have good enough models, it is imperative to start incorporating them into NLP applications, like the ones that I presented like summarization, argument mining, and misinformation detection. Thank you. I'm happy to take any questions.